Lenora Clark, Director of Autonomous Driving and Safety Technology for ESI Automotive. The following is a glimpse into what is actually happening when a warning light goes on in your vehicle. We will look closer at the electronic system and the most predominant failure mode. From there, I will offer a solution to extend your electronic system life. As consumers, we have high expectations for vehicle design and the overall travel experience. Electric systems are the largest growth segment of automotive today, and this is directly connected to advanced safety and the electric powertrain. Car makers are innovating in areas they never expected. The systems are enabled through electronics, but we must consider the harsh environments where they need to succeed. When the electronics industry moved to lead-free, it became a clear issue for near-engine and under-hood electronics in automotive. A consortium was created to develop a more robust solder alloy. Challenges were experienced in thermal cycling, showing weakness in the solder joint, and sometimes these failures were intermittent. Overall, they needed a more reliable solder joint. So you're driving along and everything seems fine, then all of a sudden a warning light goes on. Maybe you have a car where the warning light goes on for a few days and then goes off. I actually had that car. Let's take a look what's actually happening. The warning lights on your dash are connected to various systems throughout the vehicle through a series of wires called the vehicle architecture. If we follow the architecture to the system in question, you will see a box. All electronic systems are protected by an external box. But let's break it open. Inside, it reveals a printed circuit board assembly. The IC substrates, the components, are joined to the circuit board. And it is this union that is the weakest location in the build. In most cases, the component is joined to the circuit board using a metal alloy. It starts as a paste and when reflowed melts into metallic alloy, adhering the parts together. We call this interface the solder joint. The challenge is that the component and the circuit boards have very different properties when heated. Various materials to make up each will heat and expand at different rates. We call this the coefficient of thermal expansion, and when they're different, we call it a CTE mismatch. Parts move in different directions at different rates, and the pressure is put on the solder joint. That pressure eventually forms a crack. And depending on the performance necessary for the system, a small change in resistance as a function of this crack could cause a failure. If a small change in resistance is not a problem, eventually the crack will continue to propagate and cause an open, which is also a failure. The two main reasons for solder joint failure are short-term overload, where the material is pushed beyond its strength, but the more predominant in automotive is fatigue. And this fatigue is caused by loading or by thermal cycling. And thermal cycling, I'm going to call into attention, can happen as a function of location, like being close to the engine, as we discussed earlier, or through usage, when you have continuous usage of sensors or cameras, as we do in advanced safety today. So through alloy development, including solid solution strengthening, grain refinement, diffusion modifiers, and precipitate strengthening, a new solder alloy was developed in this consortium. The needle-like crystal structure of Innolot delivers a strengthened joint with enhanced thermomechanical reliability. And in turn, this gives us longer system life under harsh conditions of continuous function or aggressive environments. The SAC alloy cracks under thermal and mechanical pressure, both at temperatures above 120 degrees Celsius and as a function of the expansion and contraction pressures of the thermal cycling. As I mentioned, when electronics heat and cool as a function of processing information, or even being run in a hot environment, they start to experience the movement, that CTE mismatch. Some things move in the y-axis, others in the x-axis, and of course, different materials heat and cool faster than others, as well as some will move more or less. All this pressure was previously released in a crack in the SAC alloy. but the stronger Innolot alloy is constructed in a way to withstand the movement. It takes higher temperatures and longer durations to form a crack. This makes it a clear choice for safety-critical applications, and it is why so many Tier 1s have chosen it for its advanced safety systems. It enables them to pass OEM reliability requirements. One example is thermal cycle resistance of LED lighting. LED components function hotter than others. When testing an LED application under thermal cycles, we found the SAC alloy, represented by the blue line, starts to display failures around 600 cycles, and it continues to drop off steadily with increasing cycle exposures. The Innolot does not show issues until almost 800 cycles, and it continues to maintain a very low level of failures through 1,000 cycles. Another look is to consider design. Of course, when looking at reliability, design will also play a role in the overall system. Here, we're looking at Weibull plots. Weibull is an analysis method used for performing life data analysis. It's used to determine reliability characteristics, and in this case, we're connecting it to thermal cycle resistance. The x-axis shows the number of thermal cycles, and the farther to the right that the trend line falls, the more thermal cycles the system can endure without failure. In this case, it was a change in resistance that we were measuring. The left chart represents testing of a ball grid array with 228 input-output attachments to the printed circuit board. The right is a ball grid array with 256 input-outputs. In both instances, the Innolot represented by the red line outperforms the SAC alloy, but a closer look at the scale of the x-axis shows the characteristic life is much greater, well over 2,000 cycles on the BGA with 256 connections. So component and overall design also has an influence on characteristic life. In either scenario, the Innolot gives you a marked improvement. As we move to a platform of releasing driver responsibility to the machine, to the vehicle, the car makers are putting greater expectations on the electronic systems. Many are requiring over 2,000 thermal cycle resistance. Innolot has enabled advanced safety providers to achieve car makers' reliability requirements. Innolot extends the characteristic product life of safety systems. The alloy has more thermal and mechanical resistance and creates a stronger solder joint. And finally, Innolot has enabled many advanced safety providers to achieve car makers' reliability requirements. So not only is this alloy very good for near engine and under hood applications, but also for the critical applications of safety where function is hotter and at extended periods of time. Did you know that the Innolot alloy has already been used in automotive applications? We see it in many areas, from engine control to driver monitoring systems, used in radar sensors, and it's even used in vision systems. Currently, Innolot is being qualified for LiDAR applications. To make advances in your technology, you will need advanced materials that match your expectations. We have over 60 years experience in all market segments. We specialize in material development, and as a leading global supplier, we take pride in having a complete understanding of the automotive market's expectations with a strong focus on enhanced reliability. I thank you so much for your time. Please don't hesitate to contact me. We can continue this discussion.